This is today's green function and tangent flow and eigenvector flow, and then the Nash-Einstein's idea. I don't think I will go to formalization. There's just no time, and I actually I even want to go back to the first talk a little bit because I need to. Sorry, this is the title page. So this was the same as the last time, and so now so this is a summary of the first lecture, and I mentioned some main results, so I'm not going to repeat them for the weaker matrices, for sparse graphs, and for the band matrices. And then about the method of proof, I didn't really have time to do anything, so today I will start with method of proof. So the first thing thanks Tom, I didn't really introduce the green functions. So I want to make it precise. I think many of you probably knew it. So most people know it's in one way or the other. So the green function is 1 over h minus z. H is the matrix, and z we always use the e plus I eta. Eta is the spectral resolution. So if you look at imagined power of this the mn, which is the trace of the green function divided by 1 over n. So this is a standard quantity, and then it looks like eigenvalue minus e squared and eta plus eta squared. So this is almost like a delta functions. So you already have the delta function of all these spectral eigenvalues and with resolution eta. So eta is a parameter for resolution, and E is the energy specified which point you want to look at. Now, another quantity is the imagined part of the green function at just a diagonal part. So if you look at diagonal part, you can see that you're actually computing the J's eigenvalue at the component A. So this quantity already tell you about the size of UJA squared. So you can see that the imagined part green function is already if you can go beyond the MN, you already have information about the eigenvectors. So for example, if you know that the imagined part of green function is bounded by a constant, then you already know the green function, the eigenvalue, the eigenvector square is bounded is less than eta because this is 1 over eta. You divide over, get the eta. It's eta times c, eta times c. So if you can go to the other concept is what's the optimal eta. The optimal eta is about the size 1 over n because the eigenvalue distance is 1 over n. You have n eigenvalues in the site typically between minus 2 and 2. And so the distance is 1 over n. And so if eta is go below 1 over n, you will start to see this structure. And then this guy will not have it's very difficult to have a self-consistent equation, all this concept. So typically you need the eta to be bigger than the eigenvalue space, so they become a bit more smooth. All right, and so this is this green function. And now, so I want to just repeat this slide because this was the one we did last time, and was a bit confusing. So the idea was if you want to prove essential limit theorem, you run an Ornstein-Uhlenbeck process. And the Ornstein-Uhlenbeck process is leave Gaussian invariant. So the Gaussian is invariant. And now then the basic object is there are 2 steps. So one step is if you want to test that the ID random variables.
So just make sure that everybody understands, make sure I understand. So this is the initial random matrix we start with.
This is the initial random variable we start with.
It's just some n by n random matrix.
No, there's no random matrix anymore.
No, just some n by n matrix.
So it's just n random variables. X1 just n random variables. There's no matrix.
Right, you're not doing any matrix.
Yeah, just forget about matrix. I'm just talking about the most familiar central limit theorem. Okay, so this is a theorem that we all taught in classes about the probability theory about you just n random variable.
Yeah.
And now you want to prove the central limit theorem. And this, of course, initial data has the mean 0, and then normalize the variance is 1, which I didn't write it. Sorry. So the initial value has a mean 0 and the variance 1. And now you want to prove the central limit theorem, because now central limit theorem, then how do we prove central limit theorem? So you take a function f of this x1 plus xn divided by square root n. And if I put this one is 0, then this is the original central limit theorem is to prove that when t equals 0, this guy is the same as the Gaussian. So now I compare the time equals 0, the time equal to t. And so this is step 3. So now I look at the difference. So I start to explain from step 3. I mean, this is a bit opposite the order, but anyway. So now you look at the difference. So you take the difference, you do the Ito calculus, because now you differentiate with respect to t. Now the Ito calculus will go, you will see that second derivative will comes in. And then if you compute things correctly, this is 1 minus xj squared divided by 2n. And this factor n comes from the school, because you take 2 derivatives of square root and you get n. And now if your xj has variance 1, because you the beginning is variance 1, and for all times variance 1. So 1 minus xj squared actually equals 0. Of course, you don't worry about this correlation, but just forget about these correlations. So the expectation is equal to 1. So this term actually vanishes. And then you go to the next term. Next term will be n to the 3/2. But then you summation over here, so it's n to the 1/2. So you get n to the 1/2 times t. And if it's n to the 1/2 times t, so you know the t can go up as high as the square root of the n, then this will not change. On the other hand, you look at Ornstein-Uhlenbeck process, you know the time bigger than 1 is already Gaussian. So you choose this t slightly bigger than 1, and you know this x1 of t plus xn of t, each one is Gaussian already. So this guy will be Gaussian, and the error will be small, and so the t equals 0 term will be Gaussian as well.
So can you explain again why the step 2?
Oh, so, the Ornstein-Uhlenbeck process.
But the Ornstein-Uhlenbeck process
has why this one will converge to Gaussian at time p equal to 1, right? So you want to know why this is correct. When t is not much bigger than 1, then it's a Gaussian.
So you're saying if t is much bigger than 1, and now I take more and more copies of xn. No, I just look at one copy. You take one copy of Ornstein-Uhlenbeck process, just one, any one. And then you look at time, t is much bigger than 1. Then you already know that no matter which initial data you start from, at the time t will be a Gaussian. I see. So there the law.
Initial data.
Saying you're taking a bunch of Gaussian, you're taking the average of a bunch of Gaussians, so it's approached. This would be a Gaussian.
That's right. It's what I'm saying is at the time t equals 0, you don't care about what's the initial data. At the time t, the Ornstein-Uhlenbeck process will make you already into a Gaussian. And now if each xi is a Gaussian, then of course their sum is also a Gaussian. So I will
this time tends to infinity.
You don't need time tend to. Sorry, you don't.
The approach is when time tends to infinity.
Actually, you only have the time that is much bigger than 1.
There are two things which go to infinity: t and n. When
That's
say
right.
approaches Gaussian is when t tends to infinity.
I mean, this the step 2. The step
The
2
word approaches in what limit? T tends to infinity or n tends to infinity?
Oh, I see. So it's angled to infinity. Because your theorem, the theorem you want to prove is angled to infinity. So you have to choose your t depending on n, like n to the epsilon. And then you take angle to infinity. So now here, what I'm trying to say is there are two things happening here. One is the comparison of the change at time t equals 0 and the time equal to t. And the other one is that you have to ask yourself that now how fast your ergodicity hold in time t. So ergodicity, I want the ergodicity here hold to be in time n to the epsilon because here I know if t can go as high as n to the square root of the n. And now here I know that t, as long as t is n to the epsilon, each individual one is already become Gauss. And so these two things put together, then it's a Gauss. Yes.
I guess this is not very relevant for what comes next, but in the third step, there's also an integration by parts going on.
Yes.
Because the Ito also gives you an F prime coming from
Yes.
the drift term, and you convert it to F double prime times x squared. So it's just in integration by parts.
That's right. Yes.
Okay.
So I didn't do that because this is the,
I don't want to show calculation on the blackboard.
so you're right. This X I of T, this is first order term. But I do integration by part. This is how this X come from.
Thanks. All right. So now for the random matrices. Now what has to be done is I change I define the metric Brownian motions. And the metric Brownian motion is you just let each metric element as independent Brownian motion up to because it's symmetric metric, it is symmetric. And now if you want to the similar concept of Horng-Tzer and Uhlenbeck, symmetric Horng-Tzer and Uhlenbeck, you still subtract a drift term. After you subtract drift term, then this one will still have a Gaussian as invariant. All right. Now, so now you look at the time t. At time t, the Horng-Tzer and Uhlenbeck process can be solved exactly. So at time t is the initial data h0 to e to the minus t over 2 and plus square root 1 minus e to the minus t times this Brownian motion part. The Brownian motion part will become the GOE. So roughly speaking, if you solve the Horng-Tzer and Uhlenbeck process, the probability distributions is go like initial data plus square root t plus GOE. This is for t small. If t is small, this is roughly like this. So roughly speaking, if you run the metric Brownian motions, what it tells you that at time t, you take initial data, you plus a tiny bit of a GOE. And this tiny bit of GOE in the modern days language is actually noise. People always use this Gaussian noise to model the noise in the data. So you take an initial matrix, you plus a small tiny noise, and this noise size is square root t if t is small. Now then the question is, now you take the metric Brownian motion like this, and then you can write down the eigenvalue and eigenvector equations. So nowadays this is it's not surprising. It's not surprising nowadays, but at the time of Dyson, it was surprising that the eigenvalue satisfy the equation just depend on eigenvalue. There's no eigenvector here. The eigenvalue has a self. It's just depend on itself. On the other hand, the eigenvector also has an equation, and the equation is a case eigenvector depending on the everything else eigenvector, and then there's a Brownian. This Brownian motion. These are different Brownian motion, but anyway, there's a Brownian motion here, dBKL and UL summation over L, and then there's also a second order. There's also drift term is UK lambda K minus lambda L squared. Now, so this is called eigenvector flow. We call it E flow. And this is eigenvector, this is Dyson-Brownian motion dBm. So the metric Brownian motion was split into two equations. One is the match dBm, the other one is the E flow. And then you can check that this E flow will leave the GOE. Of course, GOE are invariant measure for this metric OU. So this will imply the high measure. This eigenvector flow will leave high measure invariant under the E flow. On the other hand, the eigenvalue also has invariant measures. The eigenvalue invariant measure is the classical Coulomb gas. And this classical Coulomb gas, there's a parameter beta here. I didn't track the beta. In this talk, the beta I always said beta equal to 1. Otherwise, there's a beta here. Right. So this Coulomb gas is invariant measure of this. So now then the question, if you compare with previous step, the question becomes the speed of these two dynamics converge to equilibrium. So the whole question just becomes a question about ergodicity of high dimension flow. And the previous one, so the previous this CLT proof is really just becomes this 3-step. So 3-step is now the first step. We need the a priori estimate on the Green's functions. And I will explain this. And then there's then the second step is you need a Gaussicity of Dyson's Brownian motion, and this icon is E flow. And so this will tell you this would. And the third step is this comparison between how this law of Green function changed under this metric Brownian motion. So the step 2, the Gaussicity, what you want is for t much bigger than n to the minus 1. So it's for t much bigger than n minus 1. Then it's already reached equilibrium. So you want to say that this green line or this blue line, so this blue line already reached equilibrium. And now the red one is comparison, is step 3. So it's completely parallel to the CLT proof
But this is how you get universality, right?
Yes,
And
this is how you
obtain universality,
Yes.
by comparing it to dynamics, to
Yes.
GOE.
That's right.
Can you say a word about the relation of this and Johansson's older approach?
I see.
Might be with
So the Johansson did something for the complex Hermitian matrices. I think what Johansson did is really the step 2.
Yeah, he added
But his time, he needed time.
much bigger.
One minus delta or something like slightly smaller than 1.
Right, but he did break it up into,
I think
he added a Gaussian, he had a GOE or whatever.
GUE. I think he did a GUE case, and I think if I remember correctly, what he need his theorem is roughly translated into t is n is some delta, and delta is small, something like that.
And you,
I forgot.
I'm not so interested in what he did, but if it fits, go back a slide.
Yes, go back. Yes.
Is it, in a way, he's not writing down your
No.
equations, but he's got some approximation to that in some range, I think.
I think what he did was he looked at the. I think he looked at the formula of the 2 metrics summed together, and there's something called the Hikami formula,
Which controls it. Yeah.
There's an explicit formula give you the eigenvalue distribution of this kind of matrix, and then he look at that explicit formula and then do a settle point calculation.
Okay, I just thought it might fit nicely to that picture.
So that's what Johansson did, and that's why the Terry Tao and the Bamboo, they can get some result because they can also combine using some of his result. But on the other hand, because the Johansson's result can do it, it's quite large here.
Yeah.
So he has lots of troubles to extend the red lines. And also there's a restriction about this has to be GOE, because the GOE there's no formula. But this is something very strange. Of course, I don't really understand, but the people has not been able to find a parallel formula for the GOE case.
It's much more complex.
And then the other thing is, I should say, this is about green function we already estimate, and actually the case of CLT is completely trivial. But on the other hand, for random matrices, you have to work a lot. And for the band matrix, actually step 1 is almost everything. This is what becomes the key of this analysis. Okay. All right. Oh, I see. I forgot to mention my co-worker.
Step 1 would be an L infinity bound on the green function.
It's not L infinity, but I will tell you what it is later on. And
Can you explain what you mean by velocity here?
Gaussicity, I'm going to say later. And also, I owe a lot to all my co-workers. I truly appreciate all, and especially Erdich has been working with me for a really long time. We've been working for 20 years. All right. Okay. So this is the typical theorem we try to prove is this kind of, this is step 1 is. We prove the trace of green function divided by n minus a semicircle. I will explain what's a semicircle later on, and has some estimate. And also the green function of the off diagonal term also has a bound. So roughly speaking, and all this is eta bigger than n to the minus 1 plus epsilon.
And you will not be able to prove any theorem like this for eta below n to the minus 1. It's just impossible because you can see from the picture for eta below n minus 1, or actually at n minus 1, you already see the structure of each individual eigenvalues, and so it's not possible. But you can do this all the way up to n to the minus 1 plus epsilon. And this mn of z is a trace of green function divided by n. And SG of z is the one you take this digital transform and you put this rho of x is a semicircle. This is if this one is a semicircle, you call it MSC. And you want to show that mn of your green function and minus MSC is less than also of diagonal term is estimate. And now the key is to prove that because the MSC satisfies the self-consistent equation, m squared plus zn plus 1 equals 0. So what you want to prove is that your mn will satisfy this equation as well.
But as you define an MSC, is it random or is it deterministic?
For MSC is this one. It's deterministic because this is semicircle.
When you take your trace like that, it's still somewhat random.
Oh, this guy is random.
Yeah.
So this is high probability. This is probability estimate. Okay. So this is the estimate of the Green's function of this. Now, so how do you do this kind of estimate? I don't have much time, but I will just show you 1 or 2 slides. So idea is that you take the green function defining equation. So this is green function defining equation. And now if you average over I, then you get mn of z. But now you look at this h times g, you have hij times gij. Oh, I see. It should be gji. So hij, gji here. And now suppose I want to see what's the dependence of hij in the gij. So I do a Taylor series of the hij. I just do a Taylor series of hij. And then I look at the defining another green function, set that hij equals 0. So I do a Taylor expansion. So Taylor expansion, I'm going to have a gij appear, and sometimes hij, sometimes sjI, because hij equals hjI. So the Taylor expansion will be in this way, and this will be OG tilde. So this hij will become hij squared, and then the term will be gii times gjj, and the other choice is gij squared, depending on you do the hij or ji case. Now, if you believe that the gii square, that if you believe the diagonal term is like mn, so this guy will be the mn, and then you have the gij squared term. So this is the error term. And if you let this guy equal to mn, and now hij squared summation over ij, this will becomes 1, and so this one becomes mn squared. So this term becomes mn squared, and this gij squared becomes the error term. And now the gij squared. So here, see here, the funny thing is now gij squared. Of course, you worry about how do you handle the gij squared, but the gij squared has an identity. If you summation over j of gij squared, it's exactly equal to imaginary power of gii divided by eta. So this is metric identity. So this metric identity gives you a sum rule. So this sum rule, I call it word identity because it's something similar to the, I think it's just some sort of phase invariance of the problem. So gij squared equal to imaginary power gii divided by eta. So you can see that each one of gij on the average is 1 over n eta. The gij squared is average 1 over n eta. So that's why this error term, this term becomes small, and then this guy becomes the key term, becomes the main term. So then you get this equation. Of course, I explained everything in the sense of expectation, but you need some concentration to make it work. And the error term is automatic like this. And the rigorous argument is to make this rigorous. You need the stochastic continuity argument by successively decreasing the eta, and then so this kind of procedure replaces the multi-scale analysis, and so it's actually much neater compared with multi-scale analysis. So this was the standard way of deriving some estimate on the green functions. And then compared with the standard old method is the trade, this moment method or this epsilon net. Epsilon net is combinatorial method. And so standard, but it's not particular. It's actually much more restricted in this case. So so this is the for the Wigner matrices. And now what about
How you derive the water density?
sorry,
So how is derived the water density? How you know that?
how is one?
Yes.
This one, even how this comes out?
Just for phenomenon.
This is just you just write down the green functions definition.
But it's just something soft.
Very soft.
It's just identity.
Okay, so it's just soft. So it's like nothing deep.
Linear algebra.
Okay, very good. Water density usually have more.
Yeah, no, there's nothing deep. But the key is, but what's so interesting, actually, even John again talk about it. He said, anytime this one fails, then almost the whole method fails. So the key question is, why the band matrix is so difficult is because in the band matrix, even this identity, so even this identity hold, but the GIJ, the size of GIJ is different. It's not on average. It's not. You cannot say it's not average. You only know it's the sum is less than this, but you don't know. Some of them can be big, some of them can be small. This becomes the trouble. But on the other hand, if you stay in the mean field theory, mean field type model, then you typically always get the summation. You typically has an average for free for the Wigner matrix or for the random graph model because it's mean. On the other hand, if it's not mean field, then you're in trouble because this water identity do not give you enough information.
They're still true.
It's still true, but it's just it does not tell you the individual ones. It's any information. So it's a trouble. Okay. All right. So now I don't think I can spend too much time on this because I want to go to the dynamic question. So for the sparse graph, and then you do the instead of the integration by parts, so the Taylor expansion, there's a more systematic way. You want to do the cumulative expansion, and now you have to keep track of all the higher order terms because the problem becomes a sparse graph. The reason the difference between the sparse graph and the Wigner is Wigner Hij is like 1/√n. But in the sparse case, you want to think about this guy, it's almost like 1/√d. That's correspondence. That's what you keep in mind. So when you go to a higher order, this one in higher order is start to go like n to the 1/2 square root n. If you do the power k, but on the other hand, if you do a sparse case, it's almost like this. It's almost like 1/√d to the k. But if it's 1/√d to the k, then you have to expand a lot. So there's a difficulty in the sparse.
In the case of the spark, do you take just the limit of n to infinity and this stay fixed?
Oh, there are two questions. One is you can take a d depending on n to the power, or you can take a d equal to 3 if you like. But this one, of course, is the hardest one because they're actually the square root d minus 1. So you're talking about expansion has you only have 1/√2. That's a small factor. So, all right. So now I don't have really much time to talk about this sparse graph case anyway. That you can do this.
Just say in the sparse graph case, you give a new proof. If I remember, you do give a new proof of Friedman's theorem.
Oh yes, we actually have a stronger
result.
A stronger result. It's not a,
You give a lambda 1.
yeah, we have some estimate n to the minus some constant. Yeah. And so this is for the early Serenian graph, and now for the deregulated graph, we use for deregulated graph now. I don't have.
Okay, there's what I asked you. It's right there.
So we use the switching idea. The switching idea was actually without using this switching idea, we cannot prove anything in this problem. So everything we prove in the deregulated graph depending on the switching idea.
What does that mean? You're generating a random walk on the graphs by the
No, yeah, well, yes, it's also true in terms you talk about random walk.
what happened is if you choose randomly two edge and has four vertices, and now you randomly switch them.
Yeah,
And this is the dynamics.
yeah. You're looking at this random walk on the space of regular graph.
That's right. That's right. And now this dynamics leave the still regular graph measure invariant, and this produce a new because the trouble with all these still regular graph is because once I look at the graph, then all these lines are fixed. I don't see randomness. But on the other hand, if you start to switch them, then actually the location of this guy is actually random. So this is how you introduce some sort of independent random variable into the province. And actually, I didn't know, but McKay already looked at this in 1981. I don't know what he did with this simple switching. What did he do with it? But with a lot of this, and also in the case of d bigger than or equal to 3, we have to extend this idea to a generalized switching. And instead of looking at just two randomly choose two edges, we look at a tree neighborhood, and we start to switch this boundary with some other edges. So extending this idea actually this was quite important to get down to the d equal to 3. And so unfortunately, so we are trying to lower down the d and to d finite to see if any of these results is correct for d finite. But for d bigger than or equal to 3, we only have the error estimate like this. We didn't get the Tracy Whedon yet at this point. Okay. All right. So now I want to go back. I want to go to the dynamics, and so now first I want to give you a proof of the Horng-Tzer process. Why the time equal to 1 converge to equilibrium. So this is a preceding proof, but if you look at it, so now in the first slide I talked about Horng-Tzer converge to equilibrium, converge to Gaussian at time equal to 1. So how do you prove this? So here has some fun proof. So now if you take Horng-Tzer process like this, and you take another copy, but you use the same Brownian motion, okay? And now you take a z becomes its difference. And now you look at, so the difference satisfied equation, the Brownian motion disappears, it just goes like this. dzi of t is minus zi of t, and this is of course trivial. And this is trivial becomes it's just e to the minus t of zi of 0. And this we all know what to do. So we know that for t is much bigger than 1, then the error term essentially disappears. Okay. And now, but now this is very good because now I can take my initial y of t as initial data is already as a Gaussian. But because the Horng-Tzer process keep the Gaussian, so this y of t will be Gaussian forever. And now you just wait for your x of t. So if t is much bigger than 1, you already know that x of t and y of t, which is Gaussian, already quite close. So this is a trivial proof of the Horng-Tzer process is a Gaussian. Okay. Now, so we want to mimic these ideas in the case of the Dyson's Brownian motion. And this was actually we figured this out in something like 2013 or 2014. It's after quite a few years to figure out this idea. It was now, so you take Horng-Tzer DBM like this, and now we do exactly the same thing. We take a 2 copy, and we take 2 copy, and one copy is lambda, the other copy is mu, and then we look at the C is the interpolation. Interpolation in the idea is as this interpolation parameter alpha equals 0 is one of them, and this interpolation alpha equals 1 is the other copy. And then otherwise, everything in between, then you know that as initial data is just linear interpolation between them. And now what you do is then you compare the derivative in terms of this interpolation parameters. The previous slide, I only look at the difference, but now, because now I have to look at the flow of this, the solution of this one, so I have to take the derivative of this interpolation parameters.
And because now it's slightly more complicated, so I take a derivative with respect to this interpolation parameter alpha. Now this derivative is basically just kill this Brownian motion part, and I take the derivative alpha equal to c, because c is interpolation equal to f. So I get dt of f is a difference between the f and this lambda k minus lambda t is actually becoming quadratic. So this one, it's really just formally differentiate this equation with respect to a parameter. If you formally differentiate this equation, this Brownian motion disappears, this guy becomes a square, and then the derivative of lambda becomes this guy. So derivative of lambda becomes f, derivative of lambda becomes f, and the denominator becomes square. And now, so then you look at this equation. So this equation is the equation of f, and suppose I give you Ci minus Ci. I give you the whole trajectory of Ci. And now I want to solve this as an equation in terms of f. And the reasons the reason people don't think about this was the eigenvalue lambda k minus lambda l actually is quite singular. So if this guy is singular, then you take a square, it's even more singular. And then you become such a singular equation, it's just almost impossible to do. But after some time, we start to realize, actually, this guy becomes singular. It's something we can handle. And then this dynamics, one can study this dynamics very well. And this dynamics, once you study these dynamics very well, actually give the strongest logicity you can hope to find, and this was the key. Okay, so idea is the same. The idea is the same as the previous page. So now if I can understand this interpolation flow, and then I want to show that under this flow, this function f will converge to a constant. And this one, once this converges to a constant, then you know that your lambda in the beginning of lambda, because it's interpolation between lambda and the mu, so your lambda j of t minus mu j of t is equal to the integration of this f with respect to interpolation parameter alpha, and with the right hand side independent of j. So then you know the left hand side is also independent of j. And now you choose one of them. One of them, suppose you choose mu is a GOE. Then you know that the gap of the gap of the problem you try to study, the gap of lambda j is the same as gap of GOE. So that's the idea. So the key is if I can show this one converts to a constant, and so that it's independent of j, then it's automatically tell you the gap between your models with the same as the GOE. So that's the idea. So remember the previous idea of Horng-Tzer process is no matter what's the initial data, I can compare with the Gaussian. But then for any initial data of Horng-Tzer process converge to for any two Horng-Tzer process, as the time becomes bigger than 1, this already becomes go to 0. And now here I don't show that it converges to 0, but I can show that it converges to a constant. And it converges to a constant is because this is actually a parabolic equation with very singular coefficient. So what we have is if you can show this parabolic equation with very singular coefficient converge to a constant, and then you already solve the problem. So then you ask yourself now.
So what you said there was a difficulty. It looks like there is one with the denominator. So how do you overcome that?
Oh, so now we have a question like suppose you look at the dt of u equal to greater than u. So you want to keep this in mind that this is almost a question you try to study, and d is very singular. D is singular and the time dependent. So roughly, you want to show that you want to have a parabolic estimate on the kernel, on the heat kernel of this equation. If you can have a derive some sort of parabolic estimate, heat kernel estimate on this equation, then you are done, because then the solution of this one will go to a constant. This is the idea. So
Except that doesn't look like what you have up there.
Oh, okay, this is discrete. So you think about this is as a discrete difference, and then you symmetrize, it becomes Laplace over. So,
I mean, to get back to Michael's question, you're saying now there's n and t.
yes. Yes, there's n and t.
Estimate in t. So again,
yes.
it's t some power.
Yes, yes. So you want to show that what you want to know, what you want to show is for this guy, you want to show that for t equal to n to the minus 1 plus epsilon.
Okay.
Then it's already correct. This idea. And then this why you get this? It's a bit hard for me to explain the scale.
That doesn't look like t going to infinity to me, but doesn't matter.
That's right. That's right. It doesn't look like t. You see, so the reason is the following. The reason is because the reason is t goes to infinity is the following. It's even lambda I plus 1 minus lambda I. This is 1 over n. So if you look at the square of this guy, minus 2 is n squared. And this is n squared, you divide by 1 over n. So we still have an n. And this is why this is how it works. So that's why it took a long time for us to figure out that actually the singular, when I get very close to each other, actually makes things better. And so all right. So now so I want to explain how you answer this question, and then so this one the Dyson already guess is n to the minus 1. This is actually George. I gave a talk and I think it's here.
Yeah.
And then this Alex told me that the Dyson already said it's n to the minus 1. I think, well, it's crazy. So I went to look at his paper carefully. Actually, he did say it. He said it's n to the minus 1. And anyway, so then I mentioned that we solved this Dyson conjecture, about 10 years ago. And then why am I trying to say it again? And the reason is because I think that right now this form is the optimal form, and it's very important to get this optimal form. So I want to explain the idea. What's the regularity of initial data? So I want to study the previous flow. So I defined the metric H called regular with resolution eta star. So forget about this E star. E star is the location. It's not that important. So the important one is the resolution eta star. So if something is regular at resolution eta star, it means it's a trace of green function divided by n. It's bounded above and below, and with eta bigger than eta star. So this means if you look at your spectral resolution, as long as your resolution is bigger than some eta star, and now you find then there are something. It's not too small, it's not too big. I mean, it's between two counts. It's independent of n. So this means so this rule out a situation that there's a big empty space. So suppose there's a big empty space of eta star. We find no eigenvalues, so this exclude this case. But otherwise, there's essentially no other condition. And now the theorem says if you take any initial data, you know it has a resolution eta star. It's regular. This means this is bounded. Then if I take a t bigger than eta star, forget what this r. This r has to do with this scale anyway. Then you take any time bigger than eta star, then everything becomes GOU. It's complete. So there's no other condition. So this is a bit like in PBE, you prove some sort of heat kernel estimate. Then your initial data condition is basically like just L1 condition, something like that, because it's so general, and it becomes extremely useful. And I think a lot of later development is actually depending on this concept and this result, because it tells you that you can forget about the initial condition. Basically, your initial conditions, you need some eigenvalue to be there in order to drive this into equilibrium. And on the other hand, this condition just basically says you take your ruler is eta star, and if you check every interval eta star, then you find the eigenvalue inside, and that's all you need.
So is this true for general matrices or what conditions do you have?
Then the initial data, it does not even have to be metric. You can just take endpoint. You take any endpoint. So
Yeah, okay. So, but in particular, it's true for any matrix.
in particular, it's true for any Wiegand matrix.
Yeah, it has to be a Figma matrix. You can't do it.
No, it has to be a matrix so that it has to be, this guy has to be correct.
Yes, I see.
So this guy has to be correct. So what he says is, if I give you endpoint, so if I give you some endpoint like that, then if I take a scale like eta, this is my eta star.
Yeah.
Then in this scale it looks regular. Then this scale determines how long the time you have to go.
Is this comment of Dyson connected with what he calls rigidity, spectral rigidity? You see, when he counts the number of eigenvalues in an interval where it fluctuates almost exact as you slide the interval, it's not, he hasn't commented on it.
Although I don't think it's because
At the scale of n.
yeah, because this scale eta star usually can be eigenvalue typical spacing. Suppose you say a typical spacing is 1/n. Yeah. So what we are saying is that this scale can be quite large. No matter what the scale is, then.
Are we looking at scales, some constant over n or?
Oh yes. So
Okay.
so the best we are hoping is eta star is n3 epsilon divided by n. And then this will give you the Dyson's.
But to repeat my question, you don't need to know that as long as that hypothesis is fulfilled,
Yes.
then this theorem is true. It doesn't matter whether it's a band matrix or.
Yeah, it doesn't matter what it is.
Okay.
You can just take endpoint. You just take endpoint and eigenvector. You don't even need a matrix.
Gotcha.
So it's purely a problem about statistical.
Then you have to work, then the real problem is to check that.
to check this. But on the other hand, you can imagine that if you want to check this one for eta star rather large, it's something simple.
But I think that Dyson's claim could be intuitively understood if you assume what is obviously true here, that the eigenfunctions are extended, right? Because there is a level repulsion. Basically, the dynamics are that the first order is Brownian motion due to the diagonal matrix element of the potential. The second order, by just the second order perturbation theory, has a small denominator, which is very nasty, but times a factor, which is the square of the matrix element. And at that point, the extensive nature is essential. That's the difference between dynamics in case of localization versus delocalized regime. So if you take for granted that this overlap is as it is for extended functions, that top line is essentially one-line physics intuition.
I thought that, okay, so maybe we should talk about this later. I thought that the reason, where's Dyson? The reason was if you take this guy.
Yeah, but why is it one? This one is really the overlap. It's based on the fact that the overlap of the extended states is like two Gaussian functions.
So this.
Maybe we can hold that for later.
You're going to face that when you look at the eigenvectors anyway.
Yeah,
but he's trying to prove it. Don't forget, he's trying to prove that.
But here in this orthogonal ensembles, the eigenvectors are uniformly distributed in space of vectors. If you're in the localized regime, what's here one becomes tiny number.
All right, so maybe let me summarize this quickly, and then I want to go to the eigenvectors. So this theorem actually answers this Dyson's question in sort of optimal way. And also I want to point out that actually everything about this beta ensemble people has been doing, it's actually just a special case of this result. And also two students of mine also extend this result to the edge. To the beta ensemble at the edge, to all beta. It's beta bigger than equal to 1. Okay. All right. So
Here I try to explain what the decay rate is eta, but I don't think I have much time. So I would like to talk about Nash and the Stein in the last 5 to 10 minutes. So about eigenvector flow. So you look at this eigenvector flow. So this is a flow on the orthogonal group on n dimension, and it's huge. So you look at this question, and now anyone look at this equation will think about it. This is completely crazy to try to solve this equation. This looks like much harder than the eigenvector equation. I mean, take a look. I mean, would you like to solve this equation or the eigenvector equation? So the choice is clear. You would like to solve the eigenvector equation and eigenvector equations. And now because the reason we look at this because we came from dynamics and just spending all the time on dynamics. So we look at this guy. And now I want to, so now I don't have time to state the theorem because I mentioned this in a lecture on Monday. So now you look at this eigenvector flow. So what you do is the following. What you do is you compute its moments. So you take an eigenvector, you take an eigenvector uj and j from 1 to n, and you take a projection into a fixed dimension. So you can think about this as one component, take a square. And now you compute the equation of this guy. You take its expectation of you take its moment, it's called a moment flow. And then you find that its moment flow actually is exactly the same equation as the coupling equation. This is a bit strange. Of course, coming from the same author, the same set of authors, it's not strange. But you look at if you look at so this kind of thing is actually in probability called duality transformation. And anyway, it's just a name; it doesn't really matter. So you find it's the moment actually said by this equation. But of course, if you just take a moment, it's not very useful. But what we find is actually if you take other moments, if you take eigenvector j1 to jk, and if you take it also exactly the square of the take product of them, then this one, then there's the equation in the k dimension, which is extension of this equation. Actually, this one will satisfy such an equation. And this equation, of course, is much more complicated. And I will not be able to write. I don't want to write this in details. And so this actually extends this moment flow. This is called eigenvector moment flow with this high moment. And you can have a k eigenvector. But on the other hand, you can only do this for one test vector. And then so the next thing is I want to do the k eigenvector with k different test vectors.
Can you just explain what are you conditioning on?
Conditioning on is for all the history of the eigenvalues, the whole history of eigenvalues. Because if you look at eigenvector equation, you need this guy. So I condition on the history, and so that's why you look at this equation. All right. So now for the k vector, so now I look at the k eigenvector with the k test vectors, and now I write down a horrible complicated equation. So a truly horrible equation. And now this equation is going to look like Cij times Lij. You still see this factor, lambda I minus lambda j. And this Lij is it's some sort of particle moving around, but it's of the form of Mij minus Eij. Eij is some exchange, and Mij is some vector, particle just hopping. And Mij is some exchange terms. It's quite a bit strange. So, but the key is I can still find the invariant measures. I can find the invariant measures, and I also know that
fixing k. Yeah,
for fixing k, there's invariant measures. And now this operator, even though it's not parabolic, but on the other hand, it's positive in L2 with respect to these invariant measures. And so that's why I can define the Dirichlet form. So you have a concept of invariant measures, you have a concept of Dirichlet form, but you don't have any probabilistic interpretation. So the whole thing, there's no PDE methods and there's no probability method. And if you like, it looks like this. This is some special case, and I don't think you want to see this. And then I have some video I will show you at the end if you still want to see. And so now for this complicated flow, we still can get a decay estimate like this.
is E to the minus T divided by eta star, and eta star is the initial regularity with resolution eta star. And so our task is to prove that this decay estimate with the kernel, because the previous one, I said the kernel is a constant. Now the kernel is much more complicated. The kernel now is this all invariant functions. So now there's a much bigger kernel. Kernel is actually space of rotation invariant functions, and then you show that your flow will converge to the kernel of this operator, and with the exponential decay plus error term. So I promise you to mention a few words, but now I don't about this where's the Nash Dyson come from, and now how do we prove this decay estimate in such a high dimension flow? The decay estimate for this high dimension flow has depend on two ideas. One is there's L2 decay. So now this L2 decay, I don't have time to explain in detail. But we did it with proof something in the L2 decay. And then we show that there's an estimate from L2 to L infinity. So the L2 plus L2 to L infinity decay, this one is so-called actual conjunctivities. This is something one uses a lot to get L infinity estimate from L2. And so we prove an L2 estimate. And the reason you can get L2 estimate because you see that, the flow is positive in L2, and so L2 actually is much easier. Then you get also L2 to L infinity estimate. And now here this is the last slide. I want to explain where the Nash and the Stein's idea comes in. I think it's a nice story. So for those of you who taught real analysis class, which is Alice's book, then you prove that for the heat equations, and there's a L1 to L infinity bound. It's proven by, for Nash has an idea. If you differentiate L2, you get the energy gradient of F. This is energy L2. And from L2, you get Nash inequality between 2 and 1. And the L1 is a constant. So L1 is a constant. And now you solve this equation, you get this T with K over 4 in RK. And now from this is L2 to L1 estimate, by duality, you get L infinity to L2. So this was standard in the textbook and in Alice's book. And so now you look at this proof. So you want to use this. So I try to use this in this high dimension, this complicated flow, and use this kind of idea. But now the trouble is, there are two trouble. One is we don't have a Nash inequality. So this Nash inequality from solving inequality is completely impossible to do in this discrete setting with all this L2 positivity, this flow. And the other one is this L1. This L1 is a constant in this equation is trivial, but in our case, it's not trivial because don't forget that we don't have a PDE. And so the flow do not preserve the positivity. And the L1 norm is not going to be a constant. So actually here, this is equal, actually. This is equal in the equation. So for our moment flow, we have to show that L2, this motonicity hold up to a constant. Depending on K, CK, so to a constant is still correct. And now the key, the interesting point and interesting story is now this Nash inequality, typically one proof on solving inequality. Actually, there's another proof from the Poincare inequality. And the Poincare inequality, in our case, this is our key input. We have to prove this Poincare inequality in our settings. But on the other hand, the Stein has a proof. Stein proved that this Poincare inequality actually implies this Nash inequality. So there's interesting appendix in Nash's paper. Nash didn't prove Nash inequality. It's a Stein proved Nash inequality. Okay, Stein proved Nash inequality in the Nash's appendix, paper's appendix. And so people always say Nash inequality is actually not fair to Stein. Actually, Stein was the one proved it. And but Stein, it's not just Stein proved it. Later on, everybody always use Strawberry because it's so simple. The Stein's proof is so interesting. The Stein only used the L2. This is L2 Poincare inequality. Stein find the L2 Poincare inequality actually implies this Nash inequality. And then this idea
was used a lot. I used this idea about 15 years ago in particle system. And the reason because it's in a way it's also much more dimension independent. So this Stein's idea was great. And then the difficulty is to prove this Poincare inequality also is quite difficult. But on the other hand, the whole thing can be put together and then this partial conjectivity. And this finished the second lecture. Thanks a lot. Thank you.
Well, I know you've had a lot of questions from the audience already, but maybe somebody else would like to ask some more or make some comments.
No. Yes.
Go ahead, please.
I mean, the initial data for Dyson Brownian motion helps it mix faster if it's regular. What about for the Eigenvector flow? You have no assumption on the initial data there, but if you
I assume it.
you assume the eigenvalue initial data is regular,
Yes.
but I wonder if the eigenvector initial data is not regular, does it mix even faster or does it not help?
No, it doesn't help because you are really just playing with the. I don't. You see, if you look at your equation, so everything because this guy is just L2 and then it's basically just everything.
Coefficients only depend on the eigenvalue.
Everything is in this eigenvalues. So this is something you only attempt to look at this flow until you have some confidence that you know something about eigenvalues.
I have two questions. When you're going to show us a movie, and the second was, can you say a word about Poincare inequality?
Oh, say something about Poincare inequality.
I mean, what's involved with it?
What's involved? I mean, what's involved?
Yeah, that,
This proof of Poincare inequality. Oh, this is a bit hard. This actually you look at this cube in high dimension, and the idea is now you have to figure out what's this kernel in the cube of size L and what's this rotation invariant functions, and then other than that, then it's still fairly. In a way, you figure out what's the final dimensional kernel is, and then otherwise you still using this like in the proof you just the switch it's not switching, it's step by step changing. You look at software inequality proof, you still take a line and you still try to connect there, and then you use your Schwarz to bound it. But the difficult part is really to connect all these things with the correct kernel of this projection into L dimension kernel, because this Lij tell that when you rotate them, it's invariant. You figure out what's the invariant function are, and otherwise it's not. That's what you have. And then later on you show that when L is large, then this kernel has to go back to the kernel of the full kernel L. And the other thing I can show you the movie. So this is the Eigenvector, just one color.
It's a movie of Benigni. So that's
Yes, that's right. He did this moment flow, but this moment flow just has one color. I don't know.
When we're seeing a movie,
You're seeing the eigenvector moment flow, how it changed. And then this particle, the location of the moments. So let me show you again. So you start with
there's something at the top there that we hadn't seen.
you start with something like here. Okay. So now here this particle. This particle mark the location of this U6 to this. I think it is 3 point here. And then they fall into 2 point. And then this is 9, 3, and this 1 here. So these are their locations. And now you want to see how the location change under this flow. And this is how they change. But this is not my. It's not done by me. I mean,
At the top there, the movie's at the top, right? Those lines are the eigenvectors.
yeah. This is the This is the
They're not crossing, right?
Yeah, no.
No, okay. Right, okay, so I have to thank these young people can do it. I wish somebody can make a color flow. It's much more interesting.
Can I ask a quick question? So you had that for the initial data, the condition with a little c that says you have no big gaps.
Yes, that's right.
Now, if you have a small number of big gaps,
Yes.
anyway, most of the eigenvalues will not be close to a gap because they'll be in the like condensed parts. So I'm wondering, like maybe some kind of pigeonhole principle is going to tell you there can't be too many big gaps, right? I mean, at most points, you know, you do have a little c just by dumb pigeonhole principle, but most eigenvalues are actually going to be like far away from those gaps if you have them. So it makes sense that maybe you don't need this condition.
Oh, it's we are trying. What we are trying to do is because it's we're trying to say we're trying to look at the local theorem. Local theorem means our theorem assumption is if I look at energy E, take a distance R, then I look at something here inside here. So then there's a concept of eta star, which is an interval here.
Okay, I see. You want it for every E, but if you just want to say for most pairs of consecutive eigenvalues, the distances are correct, this will be okay.
Sorry. But
Okay,
I
okay,
want to
got it.
just look at this.
Yeah. Okay, you're looking at more like sensitive.
And the reason I want to fix the energy E and this distance because this Uhlenbeck, you remember that George Uhlenbeck has a complaint that about this global law is completely wrong. And why can something correct in the second order? And this also answers the Uhlenbeck's question because the problem is local, and so you don't have to worry about the global law.
But does everything you do also imply that if I take a typical pair of consecutive eigenvalues, then like the distribution of the distance between them is like what you have for, yeah, okay.
Okay, well, let's thank Yau again for